We're going to take a look at samples of solving exponentials and logarithms that we've done during the course of this unit. So many of these samples, if you follow this pattern of recognizing what the problem looks like and which technique to use, it might help you in getting the problem solved quicker. So this first set, if you want to look at these and recognize that we can convert these from either exponential to log or log to exponential, that will help you start the problem. So this first one, we're going to take and we're going to make this into a log. So it's going to be log base 4 of 19 is equal to x. Now if we're going to do the change of base theorem, make this log of 19 over log of 4 is equal to x. So x will equal approximately, when we do that on our calculator, 2.12. Now the next one, it's a logarithm problem, so I'm going to convert it to an exponential. And if we use our circle tour, again, you just go like this to get the setup. You go 125 to the 2/3 power is equal to 2x plus 4. If you do 125 to the 2/3, you could do that on your calculator or recognize that the cube root of 125 is 5 and then square it, you get 25. That equals 2x plus 4. Subtract 4 from both sides, you get 21 equals 2x. So x is going to equal 10.5 when you take half of both sides. If you put that number back into the original, it checks. Because it's a log, you want to check to make sure you're not taking the log of a negative or 0. Now the next one, we should recognize that this will start off by using one of our properties of logs. The property of logs that I'm going to use is that if we have log base a of c minus log base a of d, that's going to equal log base a of c over d. So we're using that property, if we recognize that subtracting logs with the same base means you can divide the numbers on the inside. It's going to be log base 2 of 3x over 27 is equal to 4. 3x over 27 is going to equal x over 9. So if I go log base 2 of x over 9 reduced equals 4. Then we're going to set it up as an exponential. So we're going to have 2 to the 4th is equal to x over 9. If I solve that, 2 to the 4th, and then I multiply that by 9, I'm going to get x, that's 16 times 9, x is going to equal 144. And if we put 144 back into the original where there's an x, notice that we won't get negative or 0, so it does check out. Let's try the next one. These are the patterns when you have the same base on both sides. It might be both the same base on logarithms, or it might be the same base on exponentials. When that's the case, when the same base on logarithms, you can set the inside part of the logarithms equal to each other. Then we just solve this equation. I'm going to subtract 2x from both sides. I'm going to add 8 to both sides, so we get 2x equal to 18. And then divide by 2, you get x equal to 9. You should put this back in to check to see if it gives you a 0 or a negative, and it does not, so 9 does check. This other one I'm going to do, I don't have to check this one because it's an exponential, but I'm just going to solve the equation by setting the exponents equal when the bases are the same. So I'm going to subtract x from both sides, I get 4x. I'm going to add 20 to both sides, I get 4x equal to 24. Divide by 4, you get x equal to 6 for an answer. Now, the next pattern we're going to look at is when you don't have the same bases, but you can get the same bases on both sides. So this one, what we're going to do is, I notice that both of these we can make into 5 to a power. So 5 cubed is equal to 125 to the 10x plus 4 power. And then 625 is 5 to the 4th power. So I get 7x minus 2 as the exponent. So now when I distribute through, multiply the exponents together, I get 30x plus 12 for this side. And on the other side, I get 5 to the 28x minus 8 on this side. Now those, I can set the exponents equal to each other. And so I'm going to have 30x minus or plus 12 equal to 28x minus 8. I'm going to subtract 28x from both sides. I'll get a 2x. Subtract 12 from both sides. I get a negative 20. Divide by 2 on both sides. You get x equal to negative 10. We started with an exponential, so you don't have to worry about checking this in a logarithm. All right, the last one is one of the types of problems that you have to do several steps. There are a couple ways to do these. I'm going to use the exact method way, where I'm going to go ahead and do the problem. I'm going to not do any logs until the very end on my calculator. So you're going to see the work develop where the logs are going to stay in the problem. So first of all, when you have two bases on both sides and you cannot get those bases to be the same, 6 and 9 I can't make into the same base, I'm going to take the log of both sides to get, because logs can allow us to bring exponents down. And the variables being in the exponent means I'm going to want to get that exponent down. Now I could take the log, any log of both sides. I'll use the common log. I'm going to bring the exponent down in front, so x plus 5 times log of 6 is equal to x times log of 9. Next, I want to go ahead and distribute through the log of 6, so I'm going to have x times log of 6 plus 5 times log of 6 is equal to x times log of 9. Now, in this case, when I get to this stage, I want to gather the x terms on the same side. So I'm going to subtract the x log of, I need to keep my 6 here, so x log of 6, I'm going to subtract it from both sides so that both of them that have x's in them are on the same side. So I'm going to be left with 5 log of 6 on this side, and have x times log of 9 minus x times log of 6 over here. Now once I have that, I can go ahead and factor out an x on this side, on the right side. So great common factor of x. So we have log of 9 minus log of 6. Now I can divide by log of 9 minus log of 6 on both sides. So I'm going to have 5 times log of 6 divided by log of 9 minus log of 6 equal to x, which is left over once I divide that. Then I've got to do this on my calculator. I'm just going to remind you, you need to make sure you put a parentheses around that denominator. Otherwise, you're going to lose the order of operations there. So when we do that on our calculator, we get about 22.1 as an answer. This one is an exponential to start with, so you don't need to check it because it's not a logarithm. So these outline several of the patterns of the types of logarithm and exponential problems that we solve. The patterns tend to fall in the category patterns that you can convert from exponential to log or log to exponential. You might want to use the properties of properties of logarithms in the process. Also, we have the ones where the bases are the same. You just set the individual pieces equal to each other and solve. Also, we have the ones where you can get the bases to be the same. And in that case, you get the bases to be the same, and you can then just set the exponents equal once those bases are the same. And then lastly, what if you can't get the bases to be the same? Well, the advantage of logs is if you do the log of both sides, the exponents come down, and you get the variables out of the exponents, you can do some distribution, some solving, and you can get your answer for this common type of problem.